Okay, welcome everybody. Also, as a Dean of Aerospace Engineering, it's an honor for me to welcome Walter Lewin here, and I would also like to say on behalf of the Executive Board of the University, a special welcome and our gratitude for that you are willing to be here and give us this lecture today. This all started about 2 or 3 years ago at a breakfast during an off-site meeting with deans and directors when Anka Mulder and I and Daan Lenstra were discussing the excellent physics lectures of Walter Lewin on the web, which are world famous for their quality, their didactic quality, and their inspiration they give to people in the USA, but actually worldwide. And then we thought, wouldn't it be a nice idea to invite him to Delft? Would that be possible? And today he's here. There was a few years in between. The reason for that was that actually there were some health problems in between, and at some point I've learned this week that Walter's family was told that he had only 48 hours to live and actually had 3 consecutive heart surgeries in a very short time. So it makes us extra grateful that you are here today. Because I've been a long time fan myself and many people in the university, and so it was good to have you here. It started all again when Anka Mulder was sitting next to Walter Lewin, because at the Open Courseware conference Walter received a prize for his contributions to Open Courseware, MIT Open Courseware. Anka Mulder was appointed as the next president of the Open Courseware Consortium, and that's why they sat together, and Anka asked again, Walter, are you still interested to come to Delft to give this lecture? You said yes, and that's why we have you here today. So he's very well known in the US by the general public, worldwide by many people who love physics and who love the lectures of Walter Lewin. But after his appearance last Monday in De Wereld Draait Door, he is now actually a star at the general public in the Netherlands. I mean, after his appearance, Twitter literally exploded. Walter Lewin was a trending topic worldwide. 600 persons tried to subscribe to the lectures today. And in 10 minutes after the Wereld Draait Door, and over 1,000 tried afterwards. So you are lucky to be here. There was also a lot of attention from the press, and I think this is rightly so. As you will see today, and I hope you will also see later on the internet, the way Walter Lewin teaches is special, is an inspiration, and the original goal for inviting him here was actually to inspire our teachers how to teach. But the goal has become much wider. As you can clearly see, the real power of Walter Lewin is to inspire everybody to love science. Of, as we say in Dutch, om van beta en techniek te houden. You make them love science. There's no choice left, right? So, I mean, that is the special quality, and I hope to see that today. There's a practical point. If you have a cell phone with you, please switch it off right now, because we don't want it to interrupt the lecture. But without further ado, I'd like to give the floor to Walter Lewin for his lecture. Okay, a short applause for him, please.
When I lecture for my students, I always try to make them wonder, tease them a little. And at the same time, I try to make it fun. And I try to make them see their own world in a different way. That's really the goal of my lectures. To make them see the world in a different way. And I thought there was no reason why I would do it any differently today. You've all looked at rainbows. And I'll bet you a nickel that most of you have never seen a rainbow. It's just like with art. Looking at art is one thing, but seeing art is something very different, because that requires education. Today, I'm going to make you see a rainbow the way you've never seen it before, and your life will never be the same. I'm going to ask you 6 questions to see what you remember from rainbows. Now those, of course, who have seen on the web my lectures about rainbows, they probably know all the answers. That's fine. And in fact, I gave many of the answers away 2 days ago at the show De Wereld Draait Door. So let's take a look at 6 simple questions. And you are lucky in a way that I like you, because my students got 16 questions to answer. So, if we can have the light down a little, then we see here 6 questions. Radius. Some people may say, radius? Radius? Does a rainbow have a radius? Well, a rainbow is a perfect arc, part of a circle. So if it is a perfect circle, there has to be a midpoint somewhere. That midpoint is probably below the horizon. In fact, not only probably, almost certainly below the horizon. So there is a midpoint to that circle, and from that midpoint to the bow, then you can express that in terms of degrees. You can measure that in terms of degrees. Do you have any rough idea what that radius is? Or maybe it's different in the morning than it is in the afternoon. It's fine if that's your answer. So I want to know roughly what the radius of the rainbow is. Then, what is the color sequence? Is red on the outside? Or is blue on the outside? Or is red on the outside on Wednesday and blue on the outside on Thursday? You've looked at rainbows. Have you ever perhaps noticed that there is an enormous difference in sky brightness outside the bow and inside the bow? And I'm going to ask you to answer the question. If the answer is yes, I have, I want to know where you think the sky was brighter, inside or outside. Is there perhaps a second bow? And if there is a second one, where should you look for it in the sky? And what is the color sequence of that bow? Is there red on the outside or blue on the inside? Or does that depend on circumstances? I will excuse every non-scientist in my audience if they don't know the answer to the last question. In fact, there may even be 20% of you who don't even know what polarized light is. And if you don't know what polarized light is, then of course you cannot answer the question, are the bows polarized? So, here are the 6 questions. Who knows the answer to all 6? Just raise your hand. No one. 5. Who knows the answer to 5? Shame on you. You've never looked at my lectures on the web? There's a 5. Who knows the answers to 4? Okay, we got 3 hands. 4 hands. Who knows the answer to 3 questions? We're going to be 6, 7 people. Who knows the answer to only 2 questions? Only 6, 7 people. Who knows the answer to 1? Okay, now the real truth. Who knows the answer to none of them? All right. Look, just look behind you there. You people have looked at rainbows, but you have never seen them. After my lecture, you will be able to answer all these questions without any difficulty. And as I said, your life will never be the same. There is a law which the Dutch people think was invented by a Dutchman in the 17th century. Willebordus Snellius. And we in the Netherlands call it the Wet van Snellius. And in the United States we call it Snells Law. Almost no one knows that this law was already discovered 800 years earlier by someone else, but that's a detail. That just call it Snells Law because we're now in the Netherlands, and so it's certainly allowed to call it Snells Law. Snells Law is going to play an important role, I'm going to write it down very shortly, in the formation of the rainbow. Clearly Maxwell's equations are a must, but I will not bother you with that, because then most of you would probably leave very shortly. So let's stick for now with Snell's Law and see what happens when light strikes a drop of water. We can have more light, by the way. We can turn the lights full now. Here is one drop of water. I've made it spherical. And the sun is in the left, at the left, and light strikes this water drop everywhere. Also here, 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 here. But think about it, it's a three-dimensional object, so also here and there. But I only can make a two-dimensional cross-section. We define in physics as the angle of incidence, that is just our language, every field has its own jargon, we call that the angle of incidence. That is the angle, in this case, between this incoming light beam, think of it as a light ray if you like that, between the incoming light ray and the line which is normal, normal in physics means perpendicular to, normal to the surface. So in this case, that is the radius, which is normal to the surface, and this angle, therefore, I call I, which is the angle of incidence for that ray. But if you take the angle of incidence for this one, that's obviously 0. So as you go from here to here, the angle of incidence of the light as it strikes the rainbow increases, and I have here chosen an angle of roughly 60 degrees. You will see shortly why I chose 60 degrees. Now comes Snell's law. First, a little bit of light will be reflected. I'm not going to talk about that today. But some of that light will enter the raindrop, and we call that refraction. Don't confuse that with reflection. We call that refraction again. It's a jargon word that we use as physicists. And this is therefore the angle of refraction. And this is now where Snell's law comes in. Snell's law says that the sine of I, if you don't know what the sine is, then, well, there's not much I can do about that. Sine I equals n times the sine of r, so this is the angle I, this is the angle r, and n is what we call the refractive index. What it really means is, roughly for water, for instance, to give you an example, n is roughly 1.3, it means that light travels in water 30 times slower than it travels in vacuum. And if n were 1.5, like it is in glass, then it travels 50% lower. That is the meaning of the index of refraction. So, if we know the index of refraction for the water, and of course I need that today, and we know the angle of incidence, which we can choose. We can take 0, you can take 10 degrees, you can take any value you want to, then you can calculate with Snell's law the angle of refraction. And here you see it. This light goes into the water drop, reaches point B, and some of it escapes. I'm not going to talk about that, but some of it comes out. Some of it is reflected. Again, it's a big difference between refraction means it goes into a new medium. Reflection means it stays in the same medium, but changes direction. And when it reflects, this angle is always the same as that angle. So this is also R. So here you see it reflected. So at A it's refracted, at B it is reflected. And it reaches point C, And again, two things happen. Always two things happen. Some of it is being reflected back into the raindrop, and some of it comes out. And if you apply Snell's law, then you can show that this angle I here happens to be the same as the angle I there. So let's now look at the fact that light comes in this direction and comes out in this direction. And so I will define an angle, phi, which is the change. This angle phi here is going to play an enormously important role in the rainbow. So again, the light came in like this one, comes out like this, and we're looking now at this angle phi. Even a high school kid should be able, with very simple algebra, to show that phi equals 4r minus 2i. And I'm not expecting that you're going to check that now, just take my word for that. It's a very simple thing. For one thing, there is 1, 2, 3 r, 4 r's, and there are 2 i's, so 4i minus 2i, you know, not a bad thing. If I is 0, and I hope you all see that the line is 0, the angle between the normal to the surface and the light, the angle is 0, then Snell's law says, well, you see, r is also 0, doesn't matter what n is, so therefore it goes straight through, it reflects here, and it comes out here. So it comes out in the same direction that it came in, and indeed, if you say 4 times 0 minus 2 times 0 is 0. So phi is then 0. But now, let us look at the different values of I, and let's see what phi is going to do. If we can have the lights down a little. I have chosen here a mean value for the index of refraction for water, which I'm going to change very shortly. But this is a mean one somewhere between blue and red. The spectrum, the solar spectrum, as you all know, goes all the way, as you would say, all the colors of the rainbow, so to speak. So you have red is the shortest wave, is the longest wavelength, and blue is the shortest wavelength. And I've chosen something in the middle with an index of refraction of 1.336. And then you see Snell's law there, and you see the equation phi equals 4r minus 2i. So you pick I, any value you want to. I chose 0 to begin with. Snell's law tells you, oh, that's right. Am I doing this? The people have wired me, you see, and that's always I told you this was going to happen. I still need that laser pointer which I had in my pocket. Okay. So we have here I equals 0. And so r is 0 according to Snell's law. And so phi is 0. You've all seen that. So now I go up in I, and it's easy to calculate r because you know Snell's law, and so you can calculate phi using this equation. And as you go to higher values of I, then you see that phi reaches a maximum value. If you go further up on the water drop, then phi goes down again. This is one of the most important facts that form the rainbow. That there is a maximum value for that angle of phi. So that means you guys have to do something about this. I would say just knock one out. Excuse me? Oh, you blame me for it now. It's always the easiest, yeah. You think I have, yeah. But I don't. I have the flashlight in. The proof is my flashlight. You guys wired me up with two independent systems, and I told you that's risky. I made my point. So where were we? So this angle phi can be 0, can be 5 degrees, can be 10 degrees, can be 20, 30, 40, and then there comes a point that it can only be, that it can be no higher than 42.6 degrees. In this case, roughly 42 degrees on the rest. So it cannot come out here. Keep that in mind. This is very important what's going to come. Now, I'm going to be very specific about colors. The index of refraction is different for red light than it is for violet light. Violet is the extreme end of the spectrum. I will always use the word blue. Violet light is actually different to see in rainbows because there isn't that much in the sun, but violet light is, of course, the extreme. It's the shortest wavelengths of all. And I will tell you what the index of refraction is for red light. N equals 1.331. And the index of refraction for violet light, you may want to call it blue, it's a little higher, is 1.343. So now, you can go through a similar exercise with a different value for n, and then you can find out where are these maximum values for phi for the different colors. And they are obviously not at exactly the same location because n is different. So you find now that for the red light, the maximum value, phi max, equals 42.4 degrees. You see, you are very close to the 60 there because I went up there only in steps of 10. And phi max for the blue light is smaller. It is 40.6. And today, I will call this all the time 42, and I will call this all the time 40. But these are the exact numbers. But it's easier for me to just call them 42 and to call them 40. Now, here you see only one ray that hits the water drop at 60 degrees, but there is a huge number that hits that water drop at 60 degrees. What you could do, for instance, is you can rotate about this line the whole picture in the blackboard, take it in your hand and just rotate it around, and that figure is not going to change. The sun doesn't know what up, down, left or right is. So the sun will have light coming in here, and then there is this angle phi, but light that came in at the bottom at 60 degrees would come out there at the same restriction of the angle of phi. And so when you rotate it around, what it means is that you get a cone, you get a conical surface, because the drop itself is spherical. And so if I have now one water drop, and I have here a screen, and I have light hit a water drop, then the light that can come out, the red light, can come out at any angle, but no more than 42 degrees. So I'm going to draw that here. Oh, actually, you don't believe this, but MIT has made for me a very special triangle. One angle is 42 degrees. So why do you think that is? So, in this direction 42, in this direction 42, and then, as I said to you, it's a conical surface. So this is what is thrown back in the red color, but everywhere in between red is allowed. This is just the extreme value. This angle here is 42 degrees. Or if I do the same now for blue, then that's 40 degrees. MIT never made me one for 40 degrees. And so now, the blue light has at its extreme value this end of the cone, then this angle here is 40 degrees, and for red this angle is 42 degrees. And all the other colors in between the blue and the red fall, of course, in between the value 42 and 40. Now, what it means that if you look at the light that you see here, then all the colors are present. Because light that is here is smaller than 40 degrees, it's smaller than 42 degrees, so phi has no problem with that. Every single color is allowed within this cone, and therefore the light here will be white light. It's very important that you digest that for a minute, that the overlap of all colors your brains experience as white light. And so inside this cone, all colors can come out and you see white light. Here, however, only red. And then as you go to smaller angles, you get blue. Suppose I did an experiment and I had here an enormously strong beam of light from the sun. And I actually wanted to see the distribution of light when I just let it hit this wall again. What would I see? I would see this. I would see on the wall a circle on the outside which is red. That's this circle. And then I would see one that is blue. I would see here white light. I would see nothing here, no light, because you can't go larger than 42 degrees. Now, if there is a very smart person in my audience, and I'm sure there are quite a few, they would say, you cannot see blue. Because where there is blue, there is also red, because red can come out there. 40 degrees is smaller than 42. So at 40 degrees, you get green, you get yellow, you get blue, you get red, you get everything, so it should be white. However, it just so happens, whether you like it or not, that at the maximum values of those 5 values, the intensity of that light, so this is now phi, and I'm going to give you what red light would be doing. Red light, low values of phi comes out, and then when it hits the 42 degrees, there is a peak in it. The green comes, and when the green hits its maximum value for phi, there is a peak in it. And then the blue comes, which is the extreme end of the spectrum, and it peaks. So even though it is true that at this value for phi of 40 degrees there is also red and green, the blue dominates. And that's the reason why you actually see in the rainbow the blue quite distinct. It's an important issue that you realize that each one of those colors becomes very strong near the turning point of phi. So now we haven't seen a rainbow yet. For a rainbow, we need millions of water drops. And so let's assume that you stand somewhere. You stand here. That's you. And let's say the sun comes in like this. Sun is 150 million kilometers away from us, so all these rays from the sun are parallel. What do you see? Well, you see your own shadow. This is your shadow, here is your head. It's clear, right? Now it's raining here. And let's suppose you look in the sky in this direction. And you can pick any drop of water now, any drop of water on that line. There is one little drop here, and that little drop produces that cone of light that we just discussed. Each drop produces this cone of light. So that one does it, but this one does it, and this one, they all produce that cone of light, which is at that angle of 42 degrees. I try now to paint the 42 degrees. So this angle is 42, and this angle is 42. And you look in that direction. Will you see light? You will not see light, because it cannot be larger than 42 degrees. And this is all that's going back. So if you look in this direction, there's no light coming to you. Let's now look at a direction which is very low. Take one here. Oh. And you can pick any raindrop there as you please, anyone on this line. I'll pick this one. And now I'm going to put this 42 degrees here, and the 42 degrees here. What will you now see if you look in that direction? Come on, I want an answer. In the worst case, you're wrong. What light will you now see? Exactly. You got it. You got it. You look straight into these cones of each one of these raindrops. And so you see white light. Now I'm going to look in a very special direction. And that direction is 42 degrees away from this line. And you may pick, so this angle now is 42 degrees. I have selected that. And now I put there, again, pick a random water drop, one here. This angle is 42 degrees. And this angle is 42 degrees. What do I now see? Excuse me? Red, and only red. Cannot be blue, because you're looking exactly at you're looking at it this way. And so now you see that all the water drops here, white light, all the water drops here, nothing, no light. That means if there are dark clouds in the sky, you better believe it, you will see the dark clouds. Sky will be very dark, because the water drop is not getting any light to you. If you look here, you see all that white light coming back. So high in the sky it will be dark, low in the sky will be bright, and if you just look at the 42 degrees, you see red. So what do you think you will see when you look at 40 degrees? You see blue. And the reason why you see blue is what I mentioned, because of this peaking effect. So now, you have to realize that I don't have to look 42 degrees in this direction. I can go out of the blackboard, this is a two-dimensional cross-section, I can go out in this direction at an angle of 42 degrees. And then again, I will see only red light. So, what you have to do again, you have to rotate this figure about this axis. And when you do that, you're going to see in the sky a bow, which is red, a bow which is blue, below the bow it will be white, and outside the bow it will be dark. And so let me draw then for you what you will see. This be the center of the circle. You will see red here, and you will see other colors in between, and you will see green, blue here. And this angle is what? 42 degrees! So that's 42 degrees. And this is your shadow. If you were standing there, that would be the shadow of your head. The shadow of your head is always the center of your rainbow. And so 42 degrees from that shadow, you look at the shadow there, the sun is behind me, I go 42 degrees in this direction, red. 42 degrees in this direction, red. 42 degrees in this direction, red. 40 degrees in this direction, blue. 40 degrees in this direction, blue. And that gives me the bow. What do you think you will see here? White. The sky is bright. White light. What do you think you see here? You see dark clouds. Very dark clouds because it's raining. And so here, it's very dark. Now, I have to add something, without being as detailed as I have been. And this was already recognized by Newton, by the way. We have only looked here at rays which once refract, once reflect, and then refract out again. But you could also allow two reflections inside the water drop. And you can go through the whole physics again, turn the crank again, like this, and you will find then that you get again values for phi, which however now are not maxima, but they are minima. Don't try to see why that is a minimum now, just accept that for now. So that means you see a second bow for which the radius happens to be 52 degrees. You go through the same massaging and you find instead of 42 you will find 52 degrees. And we call that the secondary. And the secondary, so this is 42 degrees, the secondary is at 52 degrees, and with the secondary the red is on the inside and the blue is on the outside. The colors are reversed. The secondary is substantially fainter than the primary, which is one of the reasons why many of you may never have seen this, because the primary is so impressive. It asks all your attention. And you are sort of hypnotized by this rainbow. And you dummies didn't even notice that the inside is white and that the outside is dark. It didn't even occur to you. This dark band here, of which I will show you an example, has a name. This is very dark. It's called Alexander's dark band. I now would like to look at some slides to see whether that supports, in a way, what we have been discussing. So we don't need the overhead projector anymore. And dim the light in the usual way. Relaxed, we're not in a hurry. Dim it as much as you can, the lights. Is the dimmer not working? It's another difference between MIT and the TU. All right. First slide. First slide. Here you see what I've been telling you. You focus a little. So here's what I've been telling you, that you stand here. Here you stand. Here is that line that comes from the sun, and all that sunlight comes parallel in. It hits here a raindrop. This angle is exactly 42 degrees, and that raindrop will look red to you. You look at 40 degrees, this raindrop will look blue to you. If you have water right at your feet, which is possible, right at your feet, and if this angle were 42 degrees, you would see right at your feet red water. 42 degrees away from this line. That's all that physics demands. 42 degrees away from this line. This one is 42 degrees away from the line. You would see red. And I have done that countless times. It's great fun. I'll show you how you do that. Going to the next slide. This is the Maestro himself, Newton. You see the primary bow here. If you look very closely, you see exactly what I have done. You enter the water, you reflect in the back, and you come out in front. That gives you the primary. The secondary, you enter the water, you reflect once here, you reflect again there, and when it comes out, you get the secondary bow. And the colors are reversed, which of course is not shown here. Notice in this direction you would see your shadow, which is of course parallel to these lines. Next slide. This is how you could really feel very, very good about yourself. You imagine you're in your garden and the sun is high in the sky, that's a necessary condition, and you're spraying your lawn and you feel like a king because you're being surrounded all the way around you by a rainbow. Because look, this angle, 42 degrees, but it's also 40 degrees in this direction, and 42 degrees in this direction. And so everywhere around you, you will see red. And then you will see here blue, and then you will see here white light. And believe me, every time that I water my garden in Connecticut, where I have a house with a lot of grass, I do this every time. You always feel great when you do that. the sun has to be high in the sky, of course, to get it all the way around you. So they're really literally water drops right in front of my feet. Next slide, please. This is a painting from Turkey from the 8th century. And it's probably religious because you see here, but in the Bible it says, I do set my bow in the clouds. So it has a religious background, no doubt. Now you wonder, why is red not on the outside and blue on the inside? I think you have a choice out of three. Either the artist didn't notice that red was on the outside, and so, yeah, he just made a mistake. One possibility. The other possibility is maybe physics in the 8th century was different from what it is today. And then there is the third possibility, that the artist purposely did this for artistic reasons. I think that's what it is. He did this purposely. Next slide, please. Yeah, this is one of those silly commercials to cheat on you. Sunshine Rainbow Maker. Tell me, why is this not a rainbow? Why is it not a rainbow? I want to hear it loud and clear. Because red is not on the outside!
That I wanted to say!
You were slow. So this is not a rainbow. So this is a cheat. But nevertheless, they sell them, and so it's fine. Next one. Ah, yeah. This picture is from 1972, from January, when it was freezing cold in the Boston area. I lived in Winchester, and I was going to give my first lectures on rainbow at MIT. And I needed some slides. So I asked my daughter to go outside with me, hold a water hose in her hand, and put her fingers on it so that the water would spread out, get a lot of water drops, and I would take the pictures. Now look at this. Red on the outside, blue on the inside. You see all this white light? You now know where that comes from. And there's no light coming here from those water drops, because that's larger than 42 degrees, so you look straight through and you see the forest. Now the bad thing. The bad thing is poor Emma. Next slide. She was crying. She really was. It was freezing. But look at the result. Red on the outside, blue on the inside. Look at all this white light. My kids occasionally had to sacrifice for the sake of science. And now she appears in many books. Now she loves it. This was 1972, 28, almost 40 years ago. Next slide, please. I made this primary over my driveway in Winchester, and my goal was to also see the secondary, which is very difficult because the secondary is very, very faint. But since my background is so beautifully dark, you see the secondary here. You see the primary, red on the outside, blue on the inside, and then you see here clearly a bow whereby red is on the inside and blue is on the outside. Next slide. Picture from a friend of mine, which he took in Austria. Water from a waterfall. Red on the outside, blue on the inside. Look at all this white light. You all know where it comes from now. And outside 42 degrees, you look just straight through and you see the forest. Next slide. Ah, one of my favorite pictures, taken by Doug Johnson. This is taken at the VLA, Very Large Array Telescope in Socorro in the United States. Radio telescopes. Primary bow, red on the outside, blue on the inside. Look at the sky, much brighter here than there, very dark. Secondary bow, colors reversed, red on the inside, blue on the outside. And remember, here we have maximum values of phi. Here we have minimum values of phi. Minimum means that light can also come out which is larger than 52 degrees. That's why the sky is there again a little brighter. Because if light that comes out that is larger than 52 degrees, if all the colors can do that, you get again white light. And so that's why you have light here, this very dark band, Alexander's band, and then here the sky becomes again a little bit brighter. You can close that now. These beautiful rainbows you typically see when the water drops is somewhere between 1 millimeter and 2 millimeters. When the water drops become very small, there is another aspect that is going to be very important, which perhaps only the physicists in my audience will be able to appreciate. Light, after all, is a wave. If you have an enormously small pinhole in an opening, very small pinhole, and you shine through that a laser beam, then the light spreads when it comes out of that. And that is the result of a phenomenon which we call diffraction. Don't confuse it with refraction. It is diffraction. It has to do with the wave character of light. What I have done so far is called geometric physics. Rays, just lines, Snell's law, nothing spreads. Diffraction makes things spread. And when the water drops get much smaller than 1 millimeter, this effect of spreading is very noticeable. The red spreads out a little, the blue spreads out a little. The colors can therefore sometimes become a little fainter. But whenever you have diffraction, you have a phenomenon which is known as destructive and constructive interference. That the red color at certain locations can become totally dark, and at other locations it can be very bright. And this phenomenon of diffraction will cause then that you see in the rainbow dark lines. When you see those, you know that the raindrops were probably smaller than, say, 0.5 millimeter. I'll show you an example shortly, not yet. If now we make the raindrops even smaller, and we go to something like 30 microns, which is about the size of the raindrops in fog, it probably would not rain. Drops 30 microns, it's not rain. 100 microns, it might still rain. 30 microns, it may not rain. But you may have in the sky this fog hanging there with these 30 micron small water drops. The diffraction becomes now so important that all the colors of the rainbows are smeared out over each other. And what do you think happens when the red is over the blue and the blue is over the green and the yellow? Everything is over everything. What color do you think you're going to see? You're going to see a white rainbow. And it's often called a white fog bow, for the reason that I just mentioned, because it's rare, very rare that it rains with such small water drops. When I gave this lecture for the first time in 1972, I told you already why, my daughter, there was a student in my class, Carl Wales, who within 1 year sent me some fantastic pictures of white rainbows. He was at Fetcher Island, which was 340 miles from the North Pole at that time. And he took these pictures at 2 o'clock at night, but it was in December, so the North Pole in December, dark all the time. Oh, sorry, the other way around. He took it in July. The sun was out, and at 2 o'clock at night, when the sun was out, he took the picture of the white rainbows. And I'll show you them here on the next slide. So they were taken in the middle of the... Oh no, you're right, first this one. This one shows these dark lines. Do you see them? There's a dark line here, and we call these supernumerary bows. So this is the result of diffraction. When you see white rainbows, the diffraction is enormous. And that's the next one from Carl Wales. Next slide, please. So here you see the white rainbow taken in the middle of the night in July when the sun was out. And notice this darkness here. That is clearly the effect of what we would call supernumerary. And the next one is actually a close-up of a white rainbow. Yeah, I get it. And you see here beautifully this phenomenon of supernumerary bows. You see, really the effect of diffraction is enormous. So the white rainbow, I've never seen a white rainbow in my life, actually. I would like to ask you a question. And then I will be more patient. But I'm going to ask it to you. It's very close to sunset. And the sky is red. Everything looks red. We've seen that at sunsets. And it just so happens there is a rainbow. Why not? What do you think you will see when you take a picture?
Nothing.
You failed the course.
Overlight.
You failed the course with red light. Red light from the sun.
But if you actually make a photograph and you don't have your diaphragm correctly set, it happened to me.
Well, forget photograph. I, Walter Lewin, am looking with my own eyes. The sun is setting. I see a rainbow away from the sun. What would I see? What?
A red rainbow.
A red rainbow. What would you see inside the bow?
Just red.
That's right. No longer white. He and I were together in Delft. We lived together for 1 year. Inside the bow is no white light now because there's only red light. So inside is going to be red, but there's no reason why the red rainbow wouldn't be there at 42 degrees away from the direction from the sun. It should be red. Can I have the next slide? This is what you will see. Isn't that fantastic? So the rainbow has lost all its colors because there is no white light. But there is red. And the beauty is not only that you see here the strength of the red, the fact that it is brighter there than inside is the result of this. So that's where you see the edge, the bright red, and the other red is all this. And so you see inside the bow now red light. Okay. I think we've come to the point that we can try to answer the 6 questions. What is the radius of the bow?
42 degrees.
Yeah. What is the color sequence? And blue on the inside. Where is the sky bright? Inside or outside? Inside. Is there a second bow in the sky? Where would you look for it? About 10 degrees higher. Is the red outside or inside? red is inside. Now the last question, that was a nasty one. Remember the last question? Is the light of the rainbow polarized? When you reflect light of any surface, or from air to water, or from water to air, or to glass, doesn't matter, any kind of reflection, there is one and only one angle for the incident light. As it reflects under that angle, it comes out 100% polarized, and that angle has a name. We call that Brewster's angle. And the value of that angle depends on the index of refraction. I'll just give you a number. For instance, if you have sunlight falling onto water, that angle is 56 degrees. So when the sunlight hits that water at 56 degrees angle of incidence, that light is 100% polarized. Now, if you calculate the Brewster angle for the reflection from going from water to air, here I go from water to air, here is the air, here is the water, and here is the reflection. I'm not going to tell you the equation of the Brewster angle, although it is an extremely simple one. It only depends on the index of refraction. Damn it, of course I'm going to give you the equation. The tangent of that angle, let's call it theta, is 1 over n. If you calculate that for water, you will find that that angle, the Brewster angle, is 37 degrees. Do any one of you remember what this value of r approximately was if this is 60 degrees, which is just the right angle for the rainbow? Just maybe you remember it. This r, using Snell's law, was 40 degrees. This was 60, this was 40. Well, 40 is very close to 37. 37 is the Brewster angle. So if this angle were 37, it would come out 100% polarized, while within 3 degrees, it is almost 100% polarized. And so if you look in the sky at a rainbow, then the linear polarization here is like so, here is like so, here is like so, and here is like so. Both the primary and the secondary bow are highly linearly polarized. And I'm going to demonstrate that to you today too. If you wear sunglasses, which are polarized sunglasses, why would you wear polarized sunglasses? Why not just dark glasses? Why would you want them polarized? What? Yes. Since many surfaces in the environment, water, glass, reflect light. In many cases, not in all, are you close to the Brewster angle, and so you get polarized light coming at you, and then if you're lucky, your sunglasses may kill it. So you actually do it to suppress reflection. The direction of polarization of all polarized sunglasses is like this. That means if you wear polarized sunglasses and you look at the rainbow, you don't see the top of the rainbow because the rainbow light is polarized like that, and your sunglasses kill it. And that happened to me more than once. I walked on the beach with a friend of mine. We saw a beautiful rainbow in the water, actually, in the water of Plum Island. When both waves moved in, I saw a beautiful rainbow just for a split second. It was gone. We had to wait 5 minutes. Another wave came in. Nice rainbow. His name was Bill. I said, Bill, did you see these beautiful rainbows? He said, you're kidding. I don't see a rainbow. And I got very irritated with him. I didn't quite understand. It was so obvious at all. Until I noticed that he was wearing polarized sunglasses. I said, Bill, take your glasses off. He did, and he said to me, Walter, did you see the rainbows? I'm going to prove to you that the bow is polarized in the direction that I have indicated here. So now we've reached the point that what I said 2 nights ago to, what is his name? Matthijs Hoekkerk. Ik zei op een goed moment tegen hem, I'm going to make a rainbow with one water drop. And that's what I'm going to do now. But of course, I can really only make a rainbow if I would create rain here and I would have thousands and thousands of water drops. Therefore, what I'm going to do is not a cheat. I want you to know exactly what I'm going to do. But you will see everything I have taught you today. I'm going to do this. I have here what I call the sun. It's an enormously bright light. It's going to shine in your direction. We're going to mark it off so that it doesn't blind you. And here is one water drop. It's a biggie. But am I not allowed to make it a biggie? But it is one water drop. And that one water drop is going to do this. And we're going to put the screen down, and that's what you're going to see on the screen. You're going to see red on the outside, blue on the inside, white lights inside the bow, dark outside the bow. And then, with my linear polarizers, I will also show you that the light is linearly polarized. We have enough for those lights now. Now, you must understand that people here have been immensely kind to me because they have built this after the demonstration as I have it at MIT. And it is not easy to see this with one water drop. And so the people to whom I am really indebted, who have worked very hard on this and made it work, we think, is Peter Kikstra, Ronald van der Hoeven, and Jos Tempelman. I want to thank them very much for putting in all that time. I will tell you what the major problem is. The light has to be extremely bright. One water drop, you know, what do you expect? You need a lot of light. And we do that with a carbon arc. A carbon arc are 2 carbons, they come together, and then they discharge through the air. You get a huge amount of light. But the carbon rods get smaller because they burn up, and so they have to be brought together again. And these instruments, 100 years ago, did that all by themselves. But this instrument is probably 100 years old, and it's no longer doing that. Yes, it's still showing you the spark, but it doesn't want to do this. And so Ronald, who was crucial, instrumental in building this instrument, is going to lie here on his knees for you. And he is then going to try for maybe 1 or 2 minutes to keep the sun going. This is a protection for your own eyes. That's enough. It's not critical. Just relax for now. First this goes down. Okay. So he will turn the sun on very shortly, not yet, just wait a little. Don't expect too much. We have a saying in the United States is, you get what you paid for. One water drop. And here's my polarimeter. And so when the bow appears here, I will show you that with this polarimeter I can make the light go through and I can kill it. That indicates then that the light at that location was strongly linearly polarized. If you're ready, I'm ready. Would you want us to make it dark first, or would you like to start it in light?
Dark.
Okay, so we're going to make it immediately completely dark, and be patient, because to get the sun going is not as trivial as you may think. And then to keep the sun going is even more difficult. You got it! There's the bow! Red on the outside. Red on the outside, blue on the inside. You see this white light? You see the darkness here? Now I'm coming with my polarimeter, and I hold my polarimeter in here. The light will still go through, although it is a little reduced because of the polarimeter itself is dark. And now when I do this, you see nothing coming through anymore. And I can do it here. You see nothing going through. And when I hold it like this here, the light does go through. If you can keep the sun going for a little while, you're doing incredible, Roland. You see the red light here? Yeah! I see a beautiful red drop! One drop was red. That's why it's red here. You did great, thank you. Thank you, it was terrific. I can take this away again so that you appreciate, you know, that there was really one drop of water there. One day, it was June 20, it was 2004, I walked with my son, he was with his girlfriend, and I was with my girlfriend. My girlfriend happens to be here today, but now she's my wife, but that's a detail. So, we walked there at the Collegerama Museum in Lincoln, Massachusetts. It was 1 o'clock. Sun was high in the sky, June 20. Sun was high in the sky. And my son Chuck said, "Dad, look there!" And what I saw, I couldn't believe. I could not believe what I saw. The next slide will show you what I saw. Make it as dark as you can. This is what I saw. My head in the center, as it is, as I told you, in all rainbows, the shadow of your head is the center of the rainbow. Red on the outside, blue on the inside, white light inside the bow, and darkness outside the bow. I knew immediately that it couldn't be a rainbow, because the angle was more like 20 degrees and not 42 degrees. Being a physicist, I concluded that this could only be the result of transparent spheres. And candidates for that are small glass spheres or small plastic spheres. At the time I had no idea, but I learned later that sandblasting is done with small, very small spheres of glass, about 1.5 millimeters. And there was construction work going on there. And indeed, I saw it on the floor. I took a sample with me, of course. I wanted to know what it was. So what you see here is a glass bow. It has all the features that I have discussed today. And the only reason why the angle is 20 degrees and not 42 degrees is because the index of refraction for glass is 1.5 and not 1.33. And so when you start calculating these angles for phi maximum, well, then you get a different value. Every day, if you want to, you can see on the web a picture that is made available to you by NASA. And we call that the astronomy picture of the day. Some fantastic. In fact, when I turn on my computer, that's the image that comes up. That's the way I've said it. And so I had the idea to approach the person who produces these pictures, Robert, and I said, Robert, would you mind making this the astronomy picture of the day on the very day that I give my first lecture in the course of vibrations and waves, in which I discuss rainbows. And then ask the audience all over the world what causes this. And he did that. It was called the Mystery Picture of the Year. It was on September 13, 2004, the very day that I started my lectures. And so people were allowed to send me the answers of what they thought it was. And I just want to share with you a few of those answers. I got 3,000 responses from people all over the world. I answered them all, which took me a lot of time. There were 50 people who had really sort of the right idea. Only 2 from MIT and none from the TE. But there were really only 5 of the 3,000 who fully understood the entire physics behind it. And now I will read to you some of the answers. Very popular was, you're looking at an atomic explosion. Well, very likely, right, that Walter Lewin takes a picture of an atomic explosion which is happening right in front of his feet. Others said it's a solar eclipse. It's very popular, solar eclipse. And then there were several people who said the rings were caused by the vibration of a jackhammer. Now that's really imagination, isn't it? Red on the outside, blue on the inside, white light inside, jackhammers. Listen to this one. This is a beauty. It's the sun shining through a peephole like those you find in sex parlors. And then he put between parentheses, I know. The best answer came from a 4-year-old. His name is Benjamin. He wrote me a handwritten letter, not over, no email. And he said, you painted the picture with crayons and then you photographed it. The next time that you see a rainbow, you will check that red is on the outside. You will check that blue is on the inside. You will make sure that inside the bow, the sky is bright. You will look for the secondary. You will confirm that the outside of the secondary is blue and the inside is red. And if you happen to carry on you, as I do, 24 hours a day, a linear polarizer of your own, then you even check that the bow is polarized. This is a disease. I told you it's going to change your life, and I'm not kidding. Every single time that you will see a rainbow, You not only think about me, but you make all those tests. It is a disease that I have caused, but I cannot cure it. It can never be cured. It is a disease for life. The rainbows, for the first time, you have now seen. I told you that I often try with my students, that's enough for this one, I often try with my students to make them see the world in a beautiful way with relatively simple physics. And one classic question, of course, always comes up. Why is the sky blue and why are clouds white? If you can raise this screen, then I will write one equation on the blackboard. When white light strikes very small particles, smaller than a tenth of a micron, really very small. That's enough, yeah. Then the probability for light, so you have white light to start with, but white light consists of red, blue, yellow, green, it's all in the white light. So if that white light strikes particles which are smaller than a tenth of a micron, then the probability for scattering is 1 divided by the wavelength of the light to the power 4, and we give that the name Rayleigh scattering. And since blue light has a wavelength which is about 1.5 times smaller than red light, the probability that blue light scattered is 5 times higher than that red light scattered. In the upper atmosphere of the Earth are lots of particles smaller than 1/10 of a micron. There are naturally occurring density fluctuations of the molecules themselves. And when the light scatters of those, blue is highly preferred. So if you stand here and the sunlight comes in like this, when you look here in the sky, you see blue light. When you look here in the sky, you see blue light, because blue light is preferred because of Rayleigh scattering. Well, why are clouds not blue then? Well, Rayleigh scattering only works as long as the size of the particles is smaller than a tenth of a micron. The moment that the particles become 1 micron or larger, then there is no dependence anymore on color. They all scatter the same way. We give that a name, we call that me-scattering. And I already told you earlier with the fog bows that these clouds typically have size particles, tens of microns. So it's way too large for Rayleigh scattering. So that's why clouds are white. Light scatters of the clouds, no Rayleigh scattering. And there are several ways that I can demonstrate that. I had to do it here in a way that is not the easiest, but nevertheless, I think you will get the idea. If you light a cigarette and you look at the cigarette smoke, then in the smoke are quite a few particles smaller than the tenth of a micron. Not all of them, but quite a few. And so we're going to have a light beam coming up here, vertically up, very strong. It'll be completely dark in the lecture hall. And I'm going to hold in there a cigarette, and you will see the smoke. And I would like you to see that as bluish. I'm going to make you think that it is bluish. That would then be a reason for Rayleigh scattering. That would be a reason why the sky is blue. If you still see a little bit of whitish, well, some of the particles, of the smoke particles, are not smaller than 1/10 of a micron, and so they may well give you white light. That is phase 1 of the demonstration, that I'm going to show you blue light. I'm not going to tell you yet about phase 2. So let me first get some smoke. Okay, all lights off. Just give it a little bit of time. And I'm asking you now, and you should honestly answer. I first want to hear an answer from those who say, yeah, it looks bluish. Say yes. Yes. Now be honest and say no. No. So the no's have it, but it's very close. All right. Now I'm going to inhale this. And I'm going to put it in my lungs. And there is water in my lungs and water vapor. And so all these particles of smaller than the tenth of a micron, in no time at all, will grow to larger than 1 micron because the water will precipitate on these small particles. And so now when I blow out the smoke now, there's no Rayleigh scattering anymore. It's all me scattering. Therefore, it should be white. To make you see the difference, I do the experiment in the following way. I'm going to inhale the smoke. I'm holding it in my lungs, maybe a minute. Before I puff it out, to show you that it is white, I will again first show you this, so that you will see the difference. You ready for this? I can assure you that this is not a pleasant demonstration. So now you know, for life, you can turn the lights on again, why the sky is blue, Rayleigh scattering, and you know why the clouds are white, mis-scattering. The size of the particles is what matters. If you're now very smart, you may be able, for yourself to figure out why at sunset the light of the sun turns red. If you're smart and you put everything together, you can figure that out. If you can't, there is always Walter Lewin on the web. And you pick one of my lectures, which is actually marked blue skies and red sunsets. That is cheating, but cheating is allowed in this case. I create in the lecture hall a red sunset. It's beautiful. Kids are wearing their pants. It's beautiful. It is romantic. It's impressive. And you can see that on the web. And I hope you enjoy it. Good luck. Thank you.
So thank you very much, Walter. It was impressive. I remembered part of the rainbows, but not everything, so I didn't dare to raise my hands at 6 questions, and I wasn't the only one.
Oh, by the way, buy my book For the Love of Physics. It's all in there.
Yes, I have it.
It's all in there.
I have it and I can recommend it because there's much more in that book than you could tell today. I also would recommend to check out his lectures on the internet, on iTunes U or YouTube or the OpenCourseWare website of MIT. Thanks again very much, Walter, for this lecture. I would also like to thank the people, the team inside our faculty that made this possible. Yolanda, you emailed a lot with her to arrange everything. The people from the FMVC you already mentioned for arranging this and for marketing and communication. I'd also like to thank you all for being here today and taking their time to see this. Again, hope you will indeed love physics now, because I know that is the end goal of Walter Lewin's lecture. Thank you very much, Lewin and Walter, and
It
thank
is
you all.
allowed to ask questions. We agreed upon.
Okay,
That's
okay. I wasn't aware about it.
Maybe for
Good.
10 or 15 minutes.
So,
I may not know
any
the
questions?
answer, but you can ask the question.
We'll see. Any questions in the audience?
If anyone asks a question, there's going to be a microphone, I heard, that was going to be moved around.
Yeah, is there a third rainbow?
Is there what?
Is there a third rainbow?
Excellent question. People will think I planted that question, but I didn't. The answer is yes. The third rainbow is in the direction of the sun, whereas the other two that I have discussed are away from the sun. Sun is there, primary, secondary. The third one has radius of about 42 degrees. Unbelievably a coincidence that it happens to be the same as our primary, but it is in the direction of the sun. And when you look in the direction of the sun, you can imagine what happens. It's very faint because every reflection makes the bow fainter. The secondary is fainter than the primary. And so the tertiary is even fainter than the secondary. Yet, the tertiary, the third order rainbow, has been first seen this year. I think it was May, and was published. I want to show you a slide which will tell you how difficult it is to see the third rainbow. Look at the left part. That is what you and I would see if we look at the sun. All that white light is the light that goes straight through the raindrops. Remember that every time I told you something is reflected out, something is coming out. Well, all that light that is coming out, which I have not discussed today, that comes all out here. So here is the sun, and there it is. It's an enormously blinding light. And the actual third bow would only be this. So it has never been seen until recently, has been photographed in an incredible way. And you see, red is on the outside, and it also happens to be a radius of 42 degrees. Now the next question would be reasonable, and that is there a fourth order? The fourth order was discovered this year on October 10. And that was published even in the New York Times. It was big news. And I brought you the slide on which you see the third order and the fourth order. An enormous amount of filtering was done to get that white light under control. It's very faint, but if you have a little bit of imagination, you will see it. The next slide is the original slide of the publication. So you see here that overwhelmingly white light, which they have tried to suppress. Here you see the third order, and here you see the fourth order. The fourth order has a radius of about 45 degrees. It's a little larger, and the colors are reversed over the third order. You can see that. The red is on the outside of the third order, and with a little bit of imagination you can see that the red is on the inside of the fourth order. And people have tried to see this for more than hundreds, literally for more than hundreds of years, because it's easy with the physics to predict where they should be, because you just allow for an extra reflection inside the raindrop, you turn the crank, which was the mathematics that I showed you, out comes the angles for phi maximum and phi minimum. But of course, the simple fact that they were faint and in the direction of the sun, that's why it has taken hundreds of years before it was photographed. I give you an A+ for the question. You passed the course. Any other questions?
Maybe I missed it, but did you mention the radius of the rainbow?
Did I mention the radius of the rainbow? Are you kidding me?
That was your second or third.
Would you please come here? Did I mention the radius of the rainbow? Are you wearing glasses? You see this number? You see here the center? You see here the red? So what is the radius of the rainbow? Isn't that what you asked?
I think something is missing to calculate it.
That's the 42 degrees.
He's expecting meters.
Yeah, it's in a field of view you express a distance in degrees, in the angle. That's
Oh, you can't say it's 2 inches.
No.
You can only measure the... if I ask you how large is the sun, you cannot tell me, it's about a centimeter, that's not right. But what you can do, you can measure the angle between the left side of the sun and the right side, which is half a degree. The moon is also half a degree. So here, again, you can only express it in terms of angles. Wat? De wat?
Radius in het Engels. Hij dacht dan straal.
Yeah, but it is
Radius.
the straal. It is the
Oh,
straal.
the distance of the rainbow could be 5 centimeters if you make it in your, because the garden could be 10 miles away from you. You could be very close to a fountain, as I showed you, the one that was made in Austria. They were probably 10, 20 meters away. As long as you have water, and the sun can hit that water, unobscured by clouds, and you see that water drops, and if the water drops have the right size, you will see a rainbow. And whenever there is a fountain in any city, I always, you can read about that in my book, because I know where to find the rainbow. So I always walk so that the sun is on my back, and then I look at my shadow, and what do? I look 42 degrees in this direction. What do you think I see? Red light. I look 42 degrees in that direction. What do you think I see? Red light. And so if you know how the rainbow is formed, you can see them almost at every fountain that you have in any city, provided the sun is out. Yeah. So always you're back against the sun, and you always look at your shadow first, and it is, if this is the line to the shadow, then it is 42 degrees from that line. 42 degrees from that line. 42 degrees from that line. Always 42 degrees.
May I have the blackboard back, the one at the back? Because I have a question about that one.
Excuse me, what is the...
The question is that if you have the water drop, then also is coming water out already at the first time. Does that also generate a bow?
You mean, what is reflected the first time?
If I can see the blackboard...
Let's use the microphone here.
Or you want to see the rain, whether this produces a rainbow?
Yes.
The answer is no.
And A?
This produces a rainbow? The answer is no.
Okay, that was...
But this one is a second reflection.
Yeah.
So this one is a candidate, because it hasn't left a raindrop yet. But there, no rainbow due to this lid, and no rainbow due to this one. It has to have at the minimum one reflection inside. 2, you get the secondary. 3, you get the third order. 4 reflections, you get the fourth order. And for all these cases, you can calculate with extremely simple maths the angle's maximum phi or the minimum values for phi. I see there a hand all the way in the back. What is the question?
Do we have rainbows with moonlight?
Yes. Yes. Full moon helps because you need light. Yes, they have been seen. I'll tell you something, which is also written in my book. One day I got up late. 10 o'clock in the morning or so I got up. I took a shower. And I look, and I see a rainbow. I see 2 rainbows in front of me. 2. And both were primaries, because I can tell red was on the outside and blue was on the inside. So imagine here was I standing, water coming down, shower. Light from the sun was coming in through my window. Why did I see 2 primaries and not 1? What? Why? Because of what? No, it was only during the day. The sun was bright. I was in my shower. The sun was shining into my shower, and there were water drops, and I could touch them. I could put my hand in the rainbow, actually. And there was a beautiful rainbow here, a short piece, and there was another one very close to it. They were clearly both primaries. What?
Van verschillende kanten binnen?
The sun is 150 million kilometers away from us. So the sun comes only from one direction. It's interesting that...
I hear two suggestions from the audience.
I'll tell you.
Okay.
I'll tell you. I knew it immediately. I knew it immediately. I have two eyes. And if the rainbow is so close, then that direction, that line which I call the reference line, is different for your two eyes. Because your eyes are this far apart. So therefore, this point here, by one eye, was slightly different for the other eye. And so what I did to check it, I closed one eye, one primary went away, then I closed the other eye, and the other primary went away. So actually I had in my hands, I could touch them, I could measure them, I could say they're 7 inches long. They were right in front of me, and I had two. Two different eyes. That, of course, is never the case when the rainbow is so far away, then the distance between your eyes plays no role anymore. But when they are only a foot away from you, these two directions are different. And so the center of the two rainbows was my shadow, but it was the shadow of my eyes. And the shadow of this eye was different than the shadow of that eye because they are 6 inches apart. And this is so much fun that sometimes I purposely get up late. Seriously. And try to see these two rainbows again. Yeah, it's really great. Any more questions?
Are all water drops or raindrops perfect spheres?
What is the question? I cannot quite hear it. It's not your problem, it's my problem.
Are all water drops perfect spheres?
No. It's a very good question again. They are slightly oblate, and so it is more difficult to calculate than, depends on how oblate they are. The radius, because of that, changes a little bit, yes. It's a very good question. So this is an ideal situation that you assume they are spherical. If they're very small, it's very close to accurate, actually. But you're right, there are cases whereby it's clearly been demonstrated that the effect of the oblateness of the water drop played a role, yes. Because they come down, you know, it's the wind that they produce themselves, it's the pressure. Yeah.
What about when it is hailing or when there is snow and yet there is also the sun shining on it? Can you get rainbow then?
You should be able to answer that yourself. Because what did I say when I saw the bow on the ground? I said it must be spherical and it must be transparent. It must be transparent because it got to go in and reflect. Snow doesn't do that, hail doesn't do that. So I give you an A+ because you answered it correctly. There's another question there. Take the microphone, please.
You illustrated the rainbow for one droplet. Now in the atmosphere we have many droplets. And,
many what?
Many droplets. Many rain droplets.
Yeah?
So the light that comes out from one droplet, it can meet another droplet and then change angle.
Okay.
Is that,
if I understand your question correctly, I
yeah?
may not, and you should correct me. In this calculation, the radius of the raindrop did not come in. Unless it is smaller than 1 millimeter, then you get the supernumerary bows. But whether the raindrop is 1 millimeter, or 1.5, or 2, the calculation that I made to calculate the angle for phi max is identical, because I only allow it to be a sphere. You've nowhere have you seen in my calculations that I had to put in the radius of the raindrop.
It's not
but
my
if
question,
it's small
actually.
enough, you get diffraction and then you get supernumerary bows. Maybe that was not your question.
No, it's not my question. What I mean is, suppose that we consider one droplet, and then this light beam is coming out of this droplet, and then it's not, it's meeting another droplet. Yeah, so suppose now that we have two droplets instead of just one droplet. So maybe you can go to the picture of this droplet on the second board.
So the question is if the light that comes out of the drop meets another drop later, right?
That's a very good question. If you look in that direction, any raindrop in that direction will be blue if you look in 42 degrees. All of them along that line. And you may then, through this second interaction, you may some of those light rays from sun drops, but all others will also have to be red because the angle is 40 degrees. And so you will still see it red. But you're absolutely right that you may lose some due to a reabsorption of the red light. That's what you're saying, right? The red light that comes out is being absorbed or is being scattered away by another ray. Well, then you've lost that one. But I can assure you that since all of them along that line have to be red, the overwhelming result is still red. But it's a very good question. Yeah, it's a secondary scattering in a way. Very good question. Yeah, go ahead.
How come sunlight is white?
Is it possible to make a rainbow
I will
from...
first want to answer a question here.
Oh, sorry.
Why is the sunlight white? There's only one answer, and that is that the surface temperature of the sun is 5,700 degrees. And any object that is 37 degrees, like you and me, we radiate electromagnetic radiation, but of a very, very, very low frequency, so low that we don't even emit visible light, we only emit infrared light. And you know you do. When you hold your partner at night, you feel the warm body. That's infrared radiation. Because we are 37 degrees. If now you take a coal that you have or a piece of wood that you burn in your fire, you already get up to 2,000 degrees. Now it already begins to be emitting visible light, red light. And so the higher the temperature of a star, the more blue you will get. And if you look at the sky, you look at Betelgeuse, is red. That means the temperature is very low. It's even lower than our sun. Our sun is 5,700 degrees. There are stars in the sky which are only 2,000 degrees, and they look red. There are other stars in the sky which are 20,000 degrees surface, and they look blue. So the simple answer why the sun emits white light is because of its temperature, uniquely determined by only one parameter, and that is the temperature of the surface, 5,700 degrees. Okay, there was a question there.
Can you make a rainbow out of polarized light?
Excuse me?
Can you make a rainbow out of polarized light?
I would assume you could. Let me just think about it in what problem you would run into. If you, yeah, okay, I can draw you on the blackboard what I didn't do. I didn't want to make it too difficult. That if this light is unpolarized, that means the electric field vector, I assume that you know what that is randomly moving in all directions, right, to you. That's unpolarized light. If this is the Brewster angle, it comes out polarized like this. So the electric field vector is now polarizing perpendicular to the blackboard. Yeah? So let us assume now that you really want to be a bad boy and that you're going to use linearly polarized light here, which is 100% linearized in this direction. Then nothing will come out here. And so then you have killed the rainbow. So it depends on the direction of your linear polarization. But if the linear polarization here were like this, that's fine. Then it will reflect here beautifully and will remain 100% polarized. So it's a matter of how you do then, how you set up the experiment. Only very weird people, but I hope you are one of them, Only very weird people would want to do this. But that, I mean, you have the right spirit. That's the way scientists think. It's a very good question. And if you understand Brewster's angle, then you can give the answer for yourself. So you want to avoid to send in light that is polarized in this direction. But this is, of course, going a little bit too far. Do you know, who asked the question? Do you know what circularly polarized light is? If you say no, then I stop answering. You do not know, okay. Because with circular polarized light, it would always work. But the linear polarized light is tricky.
Mr. Lewin, oh.
Excuse me? I miss a question.
If you rotate this one, taking as you did to generate your cone, then if you have, then that angle also rotates and the polarization stays in one direction.
I missed the question, I'm sorry. It's probably not your problem, but my hearing.
In order to generate your cone on the left-hand side, you have to rotate that picture of the drop, right?
Yeah, but that's nature does that for you.
Sure.
Because the sun sees the sphere.
I agree. But now if you have polarized light like you have there, and if you now rotate it, then the polarization stays the same, but the angle rotates. So you
Well, isn't that what I told you? That's exactly what I told you. I even demonstrated it. The reason, therefore, is that here the linear polarization is in this direction, here it is in this direction, and here it is in that direction. That takes that into account. So it follows the bow. I missed the question, I'm sorry.
I think
really
the point is that the angle of polarization changes with the bow area that you look at. Is that correct?
The
The point
angle
you're
of
trying to
polarization changes with what?
It is about the difference between the two angles of the bow and the light coming in. That matters, right? That's
So
sort
this
of-
light from the sun is unpolarized.
Yes.
Light from the sun is unpolarized. And it becomes polarized, linearly polarized at this point of the reflection.
Exactly. But if you rotate it around
Yeah.
the direction, then of course the polarization also has to rotate.
And that is why you get this.
Exactly. Exactly.
So the direction of polarization
Yeah.
indeed changes because you rotate it.
That
And
was
I tried to demonstrate that to you. I held my polarimeter here, and
Exactly.
I held it here.
And that was the point, I think.
So it does
man was
change,
right.
yeah.
Yeah.
It
That was
stays
the,
always tangential along the arc. Yeah.
yeah. And that was the point
It
he was
does.
trying to make.
So the
exactly.
question is a good one. It does.
Yeah.
It's exactly this way.
Mr. Lewin, if we look at the surface of an oily pool, we also see different colors. We might see purple and green.
Jaco, can you translate it for me?
Yes.
Sorry, it's not your problem. I have a hearing problem.
Yeah,
It's always difficult in a lecture hall.
You also see different colors when you look at oil surface. You
Yeah.
see the
Yeah.
purple and greenish.
Okay.
How
it has
does this compare?
That has a name in physics. We call that thin film interference. It's a totally different phenomenon. But it is the result of the fact that you get reflection of the surface of the oil, and some light goes into the oil and then reflects from the bottom. Yeah? And then the one that comes directly from the surface is now going to interfere. So here is your oil film. Light comes in and reflects. But some of it goes in through and comes out like this. And these two have a different in phase now. Are you familiar with the fact that waves have a phase? Yeah? If the phase difference, which is the result of this, is 180 degrees, these two kill each other. And you see no light. If the phase difference, however, is 360 degrees, or a multiple of 360 degrees, then they support each other. But an oil film doesn't have everywhere the same thickness. So an oil film is more like this, say. And so you see different colors here that support each other than that you see here. It's a classic problem that we give students on an exam. So you may see here constructive interference, which is red, because this path difference is just right for constructive interference for the red, whereas here the path difference may be just right for blue light. And that's why these oils, we call it thin film interference. So that's why these oil spots have beautiful different colors.
Okay. Thanks. I think I also hear that the press wants to ask you some questions. So for now, and our students, they have to study for their exams next week anyway. So I would like to leave it as such. And again, thank you very much, and applause, please.
Okay.